Good morning and good evening, everyone. I am Salah, business researcher from Weak AEP, and today I'm going to host 53rd TrustML Young Scientist Seminar. But before that, allow me to briefly introduce Riken AEP to our valuable guests. The full name of the center, so Riken AEP, is Riken Center for Advanced Intelligence Projects. AEP was founded in 2016 as a research center for the mixed AEP projects. The center conducts Japan's leading AI research, and the center is headed by Professor Masashi Sugiyama. AEP aims to enhance AI fundamental technology and research and its real-world applications. Our center encourages collaboration with various researchers and engineers in related fields, and we'll be grateful if you could visit us in our Nihonbashi office in Tokyo in the near future. Just a small reminder is that the talk is recorded, but you still cannot use the content without the authorization of the guest. And speaking of our guests, I am very pleased to introduce Seong who's a researcher at the University of Tübingen, who will host a talk about scalable trustworthy AI, beyond what, towards, and how. And Joon, I will leave you the floor.
Right, thank you very much for the nice introduction. So it's good to see you, everyone. I don't know where you are joining from, so maybe some of you will be joining in the evening time, but it's morning time here. So good morning, good afternoon, everyone. The talk that I wish to share today is Scalable Trustworthy AI. My affiliation now is University of Tübingen. But to give you a brief overview of my previous applications, I have So I have originally come from South Korea, and then I went to the UK to study maths, and then I did my PhD in computer vision in Germany, and then I went back to Korea and worked at Naver for 3.5 years. And then now I moved back to Germany to start a group here, research group at the University of Tübingen. So I started this group a year ago, and we are still kind of expanding the size. We have 3 PhD students so far. So the topic that I wish to share today is related to the general aim of the group as well, and also the general aim that I'm personally interested in, trustworthiness of machine learning systems. To begin the story, I wish to introduce this topic as sort of transition from the what question to how question in AI. What I mean by what question or what task is given here as an example. Given an image, your task is to present a label for that. So from what point of view, you're given an image, and what you have to do is just to tell what you see in the image, for example. And this is a kind of typical predictive task. But now when it comes to how, right, you care about how you achieve the recognition, for example. So there can be different pathways where you can achieve this recognition of car through the car body, or if the training data set looks like the road is a sufficient cue for recognizing car, then probably your model will learn to exploit the background cues. And this starts to matter, right? So whether you take this causal robust pathway to recognition, or you take somewhat non-causal and maybe flaky, wobbly grounding for your recognition. And this starts to matter these days because, for example, the world is always changing, and the environment, especially the deployment environment, always changes. And so you wish to make sure that your model generalizes well to new kinds of images. But if you're taking this wrong pathway or less robust pathway, then it's probably not going to work. Just by looking at the road pixels here, the model may predict car here. So how starts to matter in this way, but also also from the trustworthiness point of view, when the model is achieving high accuracy through some unknown or not so stable means, right, then it becomes hard to trust it. Especially when your life or health or money is at stake regarding your machine learning systems. So another example, let's say you're in a self-driving car and let's say your car is driving along a cliff, and the question is whether you can lift your hands off the wheel, especially when the model doesn't seem to operate in the same way as humans would operate. So now the how matters. But here, I wish to talk a little bit about the approaches that people take to tackle this how question. So let's start the story with this simplistic toy scenario, where we try to infer how from some, let's say, typical kind of data set. So here, what data means typical pair data set of inputs and corresponding labels, X and Y. So let's say your training data looks like that. X is the image and Y is the label, and 1 corresponds to small red circle, 2 is medium green triangle, and 3 is large blue square. Okay, so if you train with this kind of data, your model will learn to pick up either of the 3 cues: size, color, or shape. Okay, and depending on which cue the model picks up, its prediction for this new sample will differ. So let's say this small blue triangle is predicted as 1. Then what is the model looking at? The scale, right? And when the answer is 2 for this model, then the model is looking at the shape. And when the prediction is 3, then we know that the model has been looking at color cue for making the prediction. The important thing here is that there is no single correct answer, because you have never told the model which cue you should be looking at. And by looking at either of the 3 cues, the model can achieve 100% accuracy on the training set. So there is nothing that stops the model from looking at either of the 3 cues. And this shows us that if you just train with what data, in the worst case, it does not include any information of how or which kind of cue the model should be looking at. So in other words, this is an ill-posed problem, hoping that the model learns how to solve a task just by watching what data, okay, the XY pair data. Aligning human intention is not very easy with this kind of data. And now let's take a look at how people address this how problem. Starting from input, I like to phrase this how problem as sort of intermediate stages that you have to kind of go through between inputs and the outputs. And that could include the cue selection or the mechanism that brings you to the correct recognition, or the reasoning steps, right? And I would like to call this previous machine learning algorithm as machine learning 1.0, so to say, where the primary focus of your model is to solve the task at all. And this is what task. And now the goal is to also learn how along with what, right? Now, if you look at the ingredients for solving how, it turns out that we are using the what data. We have been using that for machine learning 1.0, but we have not really escaped from the use of what data, even in this new phase of machine learning 2.0. And I like to question, is that right? Is that going to work at all? Okay. So I like to introduce this diagram where I show the current status quo using the what kind of data and possible upper bound using the same kind of data as before. Okay, and I like my prediction is that the upper bound here is actually not so great. And this is typical benchmarking approach that that machine learning community has relied on a lot in the past few years. In benchmarking, the important bit is the fairness of comparison, and therefore those benchmarks ensure that the participating competitors use the same set of ingredients. And in this case, the usual ingredient is the XY data set, the what data set. And here they compete for the highest accuracy, and the core contribution in terms of what they do differently is actually coming from the learning algorithm. Okay, so how to kind of, given kind of a fixed amount of ingredients, amount and type of ingredients, what is the maximal outcome you can get from it? Okay, and that used to work pretty well for what problems, as you can see from the last decade of improvements in general machine learning architectures or regularization, optimization techniques. And these are typically measured in terms of this kind of benchmark. And it's a nice playground. However, now we are trying to address a new kind of problem where we also care about how you achieve the problem and trustworthiness, a lot of topics inside that. And I feel like we are not getting as much as we could get just from the what data, and therefore we should be using more data than or new types of data than what we have been looking into. And this approach, I'd like to call it data hunting approach, where the competitors are now allowed to introduce other ingredients than the typical standard ingredients. So it's now not just XY, which are arising naturally from some distribution, but also some extra ingredients. And here the source of value is actually coming from the discovery of new efficient data sources rather than confining themselves to a confined set of data sources and trying to maximize the utility of the data. And I strongly believe this is actually the future of addressing the how task in the future. So in one sentence, to solve this how problem, we should use how data. And I like to share this viewpoint that data are some form of compression of human knowledge. Okay, so this is the diagram of how machine learning models are built in general. So there is this computational domain, and the process of training a machine learning model is some kind of transfer of knowledge from humans to machines. And there are two pathways where the knowledge is coming into the computational domain and into the models eventually. So one source is the annotators, and these annotators' knowledge or human way of solving the task is compressed in terms of data set, and that is used for training. And on the other hand, there is also a machine learning engineer who's also giving the model a lot of directions and guidance on what is the right regularization and what is the right architecture, what is the right evaluation methodology, and so on. All these kind of design choices are extracted or compressed, crystallized in the machine learning recipe that is used for validating design choices and so on. Okay. So that is kind of a nice segregation of what information and how information from humans. So typically we have been extracting what information from annotators. And when it comes to how information, such as robustness of the model, generalization, or explanation, better explainability of the model, or some uncertainty estimate, let's say, of the model, these kind of how aspects are have been encoded by the machine learning engineer in general. And the engineer sets kind of new goals, new evaluation methodologies covering those new goals, and tweaks the parameters, several knobs in the models to achieve these goals through validation. And annotators have been kind of confined to kind of giving information of the task itself. Okay. But now I like to point to the future, where we should probably also collect the how signal from large-scale crowdsourcing from a crowd of annotators. And that's going to be a new type of data set that are now appearing, but not so much. Okay, so I'm going to talk about the exact, what do I mean by how data more specifically. So I like to identify two different types of how data here. So the first is interventional data. And the other one is additional supervision on top of the original supervision. Okay, so perhaps you already got the idea of what I'm talking about. So let's talk about interventional data first. So there we are actually, we care about or we alter the generation process for the training data itself. Okay, through some human-induced intervention in the data generation process. So I'm going to give you an example here of an interventional data. But before that, I'd like to point out some specific type of spurious correlation that appear a lot in vision data sets. So let's say your task is to recognize trains in images. Then what you realize is if you look at the naturally arising data images on the web, for example, or the pictures that people normally take, you are most likely going to see trains on their rails. And therefore, if you ask the model, why did you think the image contains a train? Of course, there are strong signals around the actual train parts, but also there are quite some signals coming from the rail part. So in this case, you're solving the what task right, but the how task is probably not so great. Okay, so these parts gets quite some activations, and that's not so ideal from the how point of view. So I like to evaluate this problem from borrowing some benchmarks from the other field, which is weakly-wise semantic segmentation. Okay, so there the task is to extract the segmentation of the foreground of each object in the image just from the training with images and global image-wise labels. Okay, so in other words, you are training a classifier, but from this classifier, you have to infer the right location of the object pixel-wise. This is highly challenging. And of course, compared to training the whole system with actual pixel-wise supervision, you're going to get much less accuracy in terms of semantic segmentation. But still, comparing in this benchmark gives you a sense of how well the model is performing in terms of how task, whether the model is really looking at the foreground regions of the object, or whether it's actually looking a lot in the background, perhaps more than the foreground pixels, to make the prediction, which means that there are probably some spurious correlations in the background. Okay, so we measure the accuracy in that case through mean intersectional reunion, which is a typical measure for semantic segmentation. So here, let's talk about interventional data, what I mean by that. So to solve this kind of spurious correlations, we can think of new kinds of data, which are perhaps hard to get from some natural stream of data because those images people are not so much interested in, or not very interesting to be put on the web or to be taken really by the users. So these are the images of rails, but no trains. Okay. So having the information that these are actually background images that do not contain train is actually sufficient to tell the rails are actually not part of the train. And therefore, by knowing that, we can successfully figure out which part of this original image is actually a train and not the rail. These can be described as hard negative images as well. So we are now sampling from a new kind of input distribution, P of X, right? And with the label, negative label as well. Okay. So other types of examples come from, let's say, also from the background images, not containing the foreground object. So for the recognition of a car, let's say the road pixels are also becoming a spurious correlation. Then one solution is to collect a lot of images that do not contain a car, but contains the road pixels. Okay. Likewise for frog, let's say swamp is the spurious correlation. Then we collect swamp images without a frog. And these are hard negative training data that can resolve the spurious correlation. So now the question is how to introduce this shift in data distribution. Okay, so here's the recipe. There's no way we can avoid human effort because without human effort, there's no way we can kind of correct this spurious correlation. So the question is how to use human labor efficiently. We start with a candidate out of distribution dataset. In this case, we used open images, but we did not use any label from there. So we treat that as some kind of unlabeled stream of some random images from the web, let's say Flickr. And what we do first is to compute the probability of train the foreground object using some pre-trained classifier. There are tons of pre-trained classifiers out there these days, so we can do it. And we sort it. And the highest probability predictions will most likely contain trains like these ones. But there will also be very rare cases where there is actually no train, but still are very highly confusing for the model because it contains some strong spurious correlation like track here, or some traffic signs. Okay. And then here comes the human effort. So to tell apart which ones are actual trains and which ones are not, we need humans to actually verify it. Okay. And by human filtering, we can eventually get this set of hard negatives to be presented to the image. Okay. And here, what is actually so here you're actually looking at the results. Depending on the number of hard negatives introduced for the training of this classifier, and it turns out that you do not need that many hard negatives to make the improvement. Merely one image per class is sufficient to give you 2% point increase in MIOU score for the foreground prediction. And if you introduce, let's say, 100 images per class, that gives you 1 additional percent point. And remember that this is not a very expensive annotation compared to, let's say, drawing boundary boxes or drawing polygons for getting the object boundary, because humans just need to go through all the images here and say yes, no, right? This binary decision is super quick and just one type of your keyboard. So I would say this is a very cheap source of extra information for humans to bring about quite some gain in terms of the how task. And if you look at the improvements in different categories, you do see more improvements when there are for the classes with strong known foreground background spurious correlations like train, rail, airplane, the runway or sky, boat, water, lake, sea, right? Horse with the field, grass, and so on. So this is quite effective. So that was it for interventional data set of hard negatives. There are some other examples coming from other people's work. So I find this also very interesting, the counterfactual augmentations. So this is another annotation effort where the annotators are given a sample sentence, long, blasphemous, never have I been so glad to see the ending credits roll. And obviously the original label is negative. But now the task for the annotator is to make smallest change in this sentence to turn this sentence into a positive sentence. And by enforcing the smallest changes, number of changes, and the corresponding label, you're introducing a lot of changes in the data that you're probably not going to see in natural stream of data. So these are some examples, right? So for example, we have to turn this positive sentence into negative sentence, right? So the judgment here is fantastic originally, but now the annotator just puts supposed to be fantastic instead of fantastic. And that is kind of sufficient for them to turn the sentence's sentiment into -1. And these are hard negatives because you're not touching all the other potentially spurious correlations in the sentence, but only changing the core bit. Okay, so now they're introducing, they're kind of cutting the link between spurious features. So that I believe is a quite strong factor in introducing the half signal in the training data. The other type of interventional data that we see these days is coming from the super hot Instruct GPT and Chat GPT these days. You know, instead of training on the natural stream of data, nowadays they're starting to introduce more human intervened data sets, like asking labelers to produce answers by themselves or asking the humans to rank the different outputs of the language model in different orders, and using these additional supervision signals to train this or fine-tune this pre-trained language model. Okay, so I do believe that this kind of type of interventional data collection is actually gaining momentum and probably going to be, there's going to be a lot more interesting work in the future in this domain. And that they also report that introducing these more human signals improves trustworthiness of their models. Now coming back to the second type of how data, let's talk about additional supervision. Instead of just collecting the label bird here in this case, you also wish to collect some extra annotations from the annotators. So what are the examples of that? I'm going to show you how ImageNet annotations are made. So given a concept here, bassoon, the annotator needs to go through all the images in the page and click on the images containing the object. Okay. So in this case, the annotator is clicking on the bassoon images. There are quite a lot, actually. And here, if you think carefully about what is being collected, this is sort of all possible information that you can collect from this interface. But what people have been using so far was actually for each image, whether the image has been selected or not, true or not. So this is kind of binary supervision per image. And I like to point out the fact that this is actually discarding a lot of other possible information that could have been interesting for training machine learning systems, for example. So, for example, we also know all kinds of other information, like at which time point did the mouse enter this image and left this image, or the whole mouse track over time, right? Which is also available from the front-end system, and the record of selections. Maybe the human user select the image and then cancel it because the human thinks, the annotator thinks the image is not actually containing the image. If there has been a lot of hesitation in the selection of the image, that probably means the sample was super hard. And this kind of information about the hardness of each sample may give interesting signals for, let's say, curriculum learning of the model. Or the click location itself can also give you a lot of information about where the actual foreground cue is in the image. And that can reduce the spurious correlations with the background. As another example, I like to point you to the annotation interface for polygons for instance segmentation. So they click on the boundary of the object to get the object segment. But eventually what they use is just the binary mask of this object rather than the ordering of the click, for example. So for example, these annotators started from the top of the cat and then went to the left. And of course, for some points where it's kind of hard, the annotator hesitates more, like here. And now the annotator is relatively faster along this boundary. Sometimes the annotator makes corrections because he or she thinks, yeah, something is wrong. Okay, all these signals are kind of discarded after the annotation procedure. And my argument is that we should collect all this log of history of annotations and potentially use that for training models better. Okay, so these are kind of examples of additional supervision that are actually freely available from these systems. Okay, because the annotators are still doing whatever they are told to do as before, but now we are just collecting all the auxiliary signals from them. Okay, so the efficiency is kind of ensured. Another nice example that I always like to bring up is this OpenImage's localized narratives. So here, the annotators are producing some caption for the image. But instead of typing in the caption as they did for, let's say, Coco captions, now they are speaking as they describe the image. And while they are speaking, they move their mouse pointer over relevant regions in the image. Okay, and now the speech input is transcribed into English text. And of course, because they saved all the, they have this match between the speech time point and the location, the trajectory of the mouse over the image. They can later on link individual words in the transcribed text to different points in the image. And that gives you tons more signals of which part of the image corresponds to which terminology in the caption. So this is another nice example of efficiently collecting additional supervision from humans. So I would like to call this how dataset as well. Another example is that I'm looking into these days is, for example, sketches. I feel like Sketch is a nice interface along with text from humans. We are used to kind of typing keyboard, for example, to really describe what we want, or basically it's a nice means of communication, right? But at the same time, we draw sketches a lot to communicate with other humans, or with other humans, right? And now we wish to look at the possibility of the machines being able to recognize the sketches as well, because first, I believe Sketch is a nice interface tool for humans to express their intentions or knowledge. And two, because sketches are really nice human abstraction of the visual world. And by observing how humans are abstractifying the world and so on, maybe the machines will also know the mechanisms, the inner mechanisms of how humans are perceiving the world. Okay, so there are some initial ideas around that as well. And with this, I'd like to conclude the talk. Basically, we need more human in machine learning data. I think that's where I'm getting at. Okay, so if you look at these kind of interventional data or additional supervision, eventually there's human behind it. And so the question now is how to get more information from humans into the computational domain. And this nowadays matters a lot more, because now we're already kind of discussing about the depletion of training data. In this case, depletion of high quality training data. Because now, if you look at those large language models, they're consuming a huge amount of computing resources, of course, but also training data. And in the current trend, we're going to see those models really using the all available sources of high quality text data on the web, okay, which is estimated by this dashed line here. And the time point when this is probably going to be reached is somewhere around 2024, 2025, and so on. So what should we do when we run out of those naturally arising stream of data, right? The ultimate source of data is humans. And by tweaking the annotation procedure or prompting humans to do slightly different tasks, we can get tons more information from humans, as we have seen from the interventional data sets or data sets with additional supervision, right? So we should really now think about how to task humans to produce more data, useful data, for example, for solving this how task. Yeah, we should really think about that from now on. So that's it for the talk, and I like to take questions.
Thank you very much, Joon, for this very insightful presentation. And yeah, if anyone has a question, you can just open your microphone and ask it, or put it in the chat. I already received one question on the chat, but I also have some questions as well. But if anyone wants, I can open the questions. So you mentioned in the collection of hard auto distribution data, you had some manual intervention, but then you had some clustering step. Could you elaborate on the second part?
Right. So in the first part, we had open images, right? And then now in the second part, we have a pre-trained model so in this case, the task was to produce semantic segmentation for Pascal dataset, right? So in this case, we first trained the classifier on Pascal, and using the Pascal trained classifier for the prediction of training class, we could sort all the images in the open images dataset according to the probability of existence of train.
So whatever the wrong labels, I mean, you consider them as equal, or?
Yeah. Because you see a lot of wrong labels here, right? Because this does not contain any train, but still the model prediction was high score, and the role of human is to come into this high confidence train images and say which ones are actually containing the train and which ones are not. And we only take the ones where the model got it wrong, right? According to human.
Yeah. And this out of distribution data, you include it into the training with some kind of regularization or some kind of change in the training process?
Yeah, I did not really talk about this in the talk, so but that's a great question. So when we train a classifier, we do not normally, let's say when we train a single class classifier, there is actually no dedicated negative label, right? We only source the negative labels from the other classes, let's say, because we are using softmax. But in this case, we used, we talked about different ways of doing this. For example, introducing a negative class for every single class, or introducing a common negative class for all the classes, or yeah, I think these two are the solutions that we considered. I do not remember exactly which solution we went for, because that was what the first author decided. But if my memory is correct, we went for the solution of introducing a negative class for every class. And we assign this no train class to every negative class. So sorry, this hard out of distribution images.
I see. Thank you.
Yeah. So when we have this kind of hard out of distribution set, I think it's going to be a nice future work to look into different loss functions for dealing with this kind of new type of data. Let's say we train ImageNet with such kind of data set. What's going to be the right loss function to train with this kind of data? I think that would be very interesting as well.
That makes sense. There was a question in the chat. I will read it, but I don't understand it fully. So sometimes the background information brings meaningful information, even for human classification. Should we really force the models to discard all background information?
Yeah, that's a great question as well. The answer is no, because the background is useful. But let's say, I'm not saying we should always not look at the background, but sometimes we wish to make sure that the model is only looking at the foreground as well. There are different scenarios, basically, because let's say if we really wish to generalize well to new scenes where the spurious correlation is not really giving you any nice cue, then you should also have a choice to really use only the foreground cue. And also having a foreground only kind of model, a model that looks only at the foreground is useful, is because you can later on mix the models which are only looking at the foreground and models that are only looking at the background. Okay, so once you have those two basis functions, basically, you can freely control your combination of those two models to fit them to any new environment that you wish. So being able to purely separate out what is foreground and what is background is a nice tool for really expanding your use case of your model to novel situations.
I see.
Mm-hmm. I see one new chat here.
Yes, this one is public as well. I can read it. Thank you for your presentation. What do you think would be a good data format for recording data in the process of a human solving a task? Thank you.
So, yeah, I believe you're referring to this annotation byproducts, right? Here. So during the procedure, the annotation procedure, there can be tons of features that comes out of this. There's no unified data format for recording all this. For one thing, it's going to be a time series data because all the actions are performed in time, right? But apart from that, let's say your mouse track is XY data spread across in time. So that's going to be a like trajectory in 2D space. And for this kind of selection record, it's going to be also going to be a 2D trajectory, but more sparse because you're not clicking all the time. But at the same time, there's going to be, for example, information of who annotated it, for example, and that's going to be a not time series per se, but yeah, that could be useful as well. So there's no unified format. And because there's no unified format for addressing or for utilizing these additional auxiliary signals from annotations, you might have to come up with always new ways of dealing with it. But at the same time, now with those transformers and multimodal learning methodologies, there may be ways to treat all this information as a sort of multimodal signal, and just these are JSON strings as well, right? So you can just input the JSON string to some kind of transformer and hope that the model figures out how to make use of that nicely, right? I don't think that's really achievable in a short period of time, but eventually maybe that's also kind of interesting signals to, or interesting way to take care of this kind of signal. Thank you for the question. Yeah, thank you. There's one question from Ola Wolf. Thank you for your wonderful presentation. It was a pleasure. I'd like to ask, what novel data are you hoping for to appear in the near future? Any specific task will be more trendy in the future? Is it possible for you to speculate about it? Thank you for the question. So I'd like to give you a very nice picture of the field, but I'll go one by one. So first of all, I'd like to see more types of annotation byproducts from many types of annotation procedure. Here we have only talked about image classification. But if you look at image category labeling task as well, there are many different ways of doing that as well. For example, sometimes you give them all those 50 images at a time and then let them browse through it and click them. Or you can give them one image at a time and ask humans to produce all kinds of information on this image, like they did here, right? So from all these kind of tasks, I like to collect all these weak auxiliary signals and try to extract new kinds of information, new type of information that could also potentially be useful for solving the trustworthiness of machine learning. Okay. And that will also come out of natural language processing type of annotations like you see here as well. For example, people can start typing the answer, but there's going to be a lot of edits in between, right? And the edit history itself can also be an interesting signal to look at. And that may give you which part of the sentence was particularly hard for the annotator to do something, and so on. And in terms of the trendiness, I do see, I'm not if it's just me or many others as well, but I do see some stagnation of creation of new data sets these days. But I hope by considering these new types of supervisions, we collect a lot more interesting data sets in the future. Okay, and what seems to be also trendy these days, of course, is ChatGPT, right? And of course, we're currently looking at, for example, collecting the demonstration data right here and the re-ranking here, right? But I do believe there should be more kind of sophistication and also simplification of those tasks. From the way, I think this is going to be quite trendy as well, and there will be tons more ways to collect human input for taking care of the human feedback for training large language models as well. So I do see some trend of turning back from a bit of self-supervised learning. In the last 3, 4, 5 years, maybe, we've seen a lot of improvements in self-supervised learning, representation learning methodologies like contrastive loss and this basically self-supervision. But now I believe people should realize that, okay, that is not going to give you all necessary capabilities for the model, especially when it comes to trustworthiness. And therefore we should, because the ultimate source of trustworthiness is from humans. And I truly believe that without human in the loop, there's no way models can figure out what humans value, what human intention is, how to align with human morals, ethics, and so on. So there really has to be more methods for extracting human from humans into computational domain. So I believe there will be a bit of a reversal in this trend towards more and more unlabeled data back to humans. But this time I believe there should be more attention on how to get more efficient data from humans. Okay, because now the sheer scale of the training data itself makes it super necessary for those kind of new data sets to be small scale as well. And I do believe that's possible. We probably don't need like millions and billions of such data to really make such a change, but probably a few high quality data points are sufficient to already make the models pretty good. As you can see here, right? Only one image per class was pretty good, right? So I think that's what we are also going to see in many of the domains in the future. Thank you for the question.
The final question to conclude the talk. I had one. Just you mentioned that you believe that we're going back to more human-curated information, knowledge to improve the models. I had a question about what do you think about how do you feel about models that are bio-inspired or that use physics or differential equations or things like this that have been to improve the knowledge of the model using physical phenomena or physical system that we know?
Yeah, thanks for the question. I'm also super interested in those mathematical frameworks, right? Like I would like to say these type of methods are bringing those mathematical models into the computational domain. And I also believe those structural equations from like causality model or the differential equations from physics, right? These kind of dynamical systems are really nice crystallization of human knowledge as well. Because humans come up with those models first, and then verify their hypothesis through verification on data, right? That's how physicists build their model of the world, and economists build the causal relationships between all kinds of variables, right? And these are really nice. In a sense, models are really nice compression of training data. And I believe those equations are also really nice compression of human knowledge or human belief of how the world works. And fortunately, those equations are also, in many cases, computationally compatible. You can, for example, embed those structural causal model into nice graphical formula, graphical data structure in computers. Dynamical systems into, I don't know, there are many nice constructs in machine learning, like this neuro-ODE, for example, or all kinds of modeling tools, graphical neural network, for example. So by using those nice plug-in equations from mathematics or other domains, we should be able to achieve much better generalization, for example, because, for example, now if we know the right causal cause for some, for recognition of something, or if we can kind of already figure out what are the spurious correlations that we should probably not be looking at for future prediction, then these are really super helpful for letting the model generalize better. So yeah, I do believe there should be more collaboration, so to say, in the future between the domains, to really see which part of the equations can really be embedded into the computational domain and thus help improve the trustworthiness of machine learning systems.
Great. Thank you very much for these insights and for your question, your answers. Any final words or? Okay. I guess I will thank you again, Joon, for joining us today. It was a pleasure, and I hope that the audience as well enjoyed it as much as I did. And I'm looking forward to your new work and your research and keeping in touch with you. Thanks again.
Yeah, thank you very much for the invitation, and see you around.
And for everyone else, we have a talk on Wednesday and another one next week. So see you soon. Bye-bye, everyone.
Bye.